Another source item I want to introduce here is about the phase change of the fluid. I also use a previous example just to save time of performing the meshing and settings of the OpenFOAM. Again, if you want to see how the problem set up, you can check the previous videos of section 9 to 10. This is a simplified problem description of previous one because I simplify the solid region by only the interface, right? I don't build the aluminum 2 mm thickness, but only as interface between the hot and cold medium. What I'm going to do at this is an extra point is I want to use the hot air to heat the water as we said in the previous one, but also the water has some solid inside, which means it has some ice inside the water already, and because it's being heated, I can imagine the ice will melt and form a fluid or liquid in the next stage, right? In the final stage. So my purpose of simulation is use hot air to simulate a melting of the ice and also a fluid flow and this within the water. So the temperature change of the cold medium and also the phase change of a solid. So in the CFD simulations, they often use a very simple method called enthalpy porosity method. That means this solid is actually still treated as a liquid, but only we introduce the porosity of here, which means the fluid flow within the solid or the liquid region or special liquid region is very slow. There's very slow fluid flow in it to simulate the solid. But also because we have the temperature increase, so this solid region will change into liquid and retain all the fluid flow in the final stage. So imagine an ice formed in this fault block which has a dimension of 100, so 100 along the flow direction and also 8 millimeters in the high direction. So it still allows the fluid flow, but it will block most of the fluid flow at this stage, only leave a 2 millimeter. So because I have a 200 by 10, so the 10 is the height, only 2 millimeter gap to allow the fluid to flow. But because I use the heat medium, this region will be melting at this stage. And also you have others, if you have the hot medium and also cold region, you can also study the formation of the ice. So that is called solidification and melting source used in OpenFOAM. Again, this is the example I used before, so check my previous videos to get the previous example. And all the meshing, the split mesh regions, the temperature or the boundary settings are nearly the same, only a little bit change of the temperature. Because we have a phase change, we need to use previous setting. I use a Celsius temperature, so 220, and now I need to use Kelvin just to help introduce the phase change. So I will use this, and if you still remember the previous commands, I use this to my previous folder name called CHT simplify, and I will call back to add a source in the end, just a new name. So I will go back to my previous folder and I will find the ones so called CHT demo simplify. This is why I'm interested. So I will call back this CHT demo simplify as a new name called CHT demo simplify and source in the end. So I will copy this and I will go to my folder and check this. So this is the new ones. Again, I will delete all the results files and some extra files I will not use. And here I will change it into simplify source foam, right? And again, I said I will use all the previous settings except the temperature in Kelvin. So I will go to the boundary conditions and change everything, the air and water, the temperature into Kelvin. So currently it's 200. I use Kelvin, so it's 473 for here and 473 for here as well, right? So that's for the air, and that's only the temperature here. That is air to water. I use aluminum to define the interface. So that's for the air, and I will go to the water as well. So water, I have the temperature. If I remember before, I have 20. So 20 degree is 293, right? 293, right? 293 is 20 degrees Celsius for the water. I would also check the so that's only the temperature. So what should we do now? Because the ice has been formed in this region. Previously, we all have the region is in water or in the water liquid. Now we want this region to be specially defined as ice. So how can we do that? The only thing we need to do is to use the set fields dictionary, because to identify this region to be ice, I need to define this region with a lower temperature than the icing point or freezing point. So the ice freezing point is 0 degree with 273, right? I can define this region as minus 10 degree, right? Minus 10 degree, and then this region will have the 263 degrees, right? So I will also use so I will also enter this CHT demo simplify source. So that folder, I will use code dot to enter the VS Code. I will go to the system folder now, and I will go to the water and create a dictionary called set field dict.water. Again, the purpose of doing this is to define a region which is much lower temperature than the icing point, that will introduce the ice region, right? So the default temperature is still 293, so that is in the 0, in the water, so 293 here. And for this small region, you can just check here from 0.05 to 0.15. So that's 0.1, right? That is a region only for the water. So from here to here, that is 100 millimeter or 0.1 meter along the flowing direction, and the height is 0.08, right? So 0.08 is indicated here. So from nearly 0 to 0.08. I use a bit region higher than the setting, just make sure I include all the nodes. And that will be the region with the definition of -10. So this is actually -10 degrees C, right? I use annotation here, temperature or ice temperature. So -10 degree. Okay, so that I define here for the ice region. Now I will use this set field to override the previous settings. The previous settings is mainly about the internal field, but now my internal field is totally changed, right? The inlet is still here and all others still here, but the inlet field is different. I have a very different region with -10 degree. So I will do the operation here by using the set field dict. So set fields, I use dict. I use the system in the set fields dict dot water, and that's only in the region of water, right? So that is water region. I will enter this, and it said some internal values set to 263. If I go back here, I will go to the T. It can be seen the difference. There are some regions with 293 and some regions with 263. And for the boundaries, it's still the same. So the boundaries hasn't been changed a lot. Hasn't been changed. So the boundary field still the same. No big change, right? So that is how to define a zone that has different temperature regions. But we haven't set how to treat this region. That will be using our FV options. So I will go here and go to the water region again. So the system water, and I will create a folder named FV options. So FV options, we just copy this, and I will explain how to define this. So FV options here. Yeah, so I'm sure I have copied all this. So I name it as ice melting. I use a type called solidification melting source. So that is the source item, allowing you to define that in the OpenFOAM. And there are several main items. So the melting point is the phase change temperature for the water. We know it's 0 degree, right? I use 273.15 because I use Kelvin, and the latent heat is water is defined of ice is defined here, and also we use the heat capacity from thermal because I have the thermal defined by the constant properties, and the reference density and thermal expansion coefficient can be defined as well, and the final line is for the porosity zone or the marshy zone. which means that will introduce a very high. I can even increase more, which introduce the resistance to the water, which means the water can hardly go through this region to simulate the solid, right? And that is for our FV options for the melting or solidification depending on your scenarios by using the solidification melting source. So is that all setting? No, we still have an extra setting here because we previously used a static solver. If I go to the control dictionary here, I use CHT region simple form. This is a steady solver, but now I want to simulate ice melting, which should be a transient solver, right? So I can start from the latest time to the end time, but I need to change the FV schemes as well. So how to do that? We can just try to run from the previous or from old folder, from the tutorial folders that has been existed in the OpenFOAM. I can go to a tutorial folder. I can get heat transfer. I can use this CHT multi-region foam. So what I'm going to do is just to find one that has the solver that may apply for us for the air region and for the water region, right? I can copy these two FV schemes to my applications in the system folder for the air and for the water. Of course, we need to override these two as well in the system folder. So that should give me the if I go here, I go to the system folder, and if I open the water, I would see the FV schemes, and now I have the FV scheme, and I have the FV solutions. The solvers I'm currently using a pimple, which means it is a transient solver, right? And then I can use this as my scheme for the transient solutions. So everything should be good now, and we have redefined this, and we have the control dict, and now it's ready to run the simulation here. So CHT multi-region foam. Now the solver start run, and I will pause and see how the results is after running, because it's a transient solver compared to steady solver. It uses small steps, small time steps, and the time may be longer than the steady analysis. Leave the L note by using multi-region CHT multi-region form for transient heat transfer and fluid flow problem within the source item of solidification and melting source. The total running time is 3,000 seconds. So it's nearly or over 50 minutes. So that's really a long time for the transient problem. You know, my total running time or the total time is 500 seconds. So that's about 10 minutes, but need 50 minutes to run the simulation, right? And now we are ready to, we got results and we're ready to load the results from here. So I load the results from the calculations, and that will give me some results here of the fluid and the phase change. Hopefully that's what we are interested in, right? So if I check the temperature or the final temperature, for example, that's the final stage, I would say looks like no big difference, right? There's no big difference between the temperature with and without phase. So after loading this results file, I can see the temperature distributions. Remember, my current temperature is in Kelvin, so I can use a calculator to convert the results T into Celsius. So now it's in Celsius. Now it's temperature from 20 to 200. So that's the correct ones. And what we are going to do now is see how the melting or the phase change. So actually it has called Aus melting. So that's the source item we used, and it has alpha 1, which is actually help us to understand what happened during the process, right? So this is the initial. To make it more evident, I will only show the water region. So the gas region or the air region, I don't need that. So I will only show the water region, right? This is more evident now. So it shows in the very beginning, I have a blue zone here, which is the ice formed. Because ice in the water with minus 10 degrees, so it will also transfer the heat to the other surroundings. So it will introduce other surroundings. And also because this is a 50, so after 1 minute, also there's some heat bring from the right side and from the top side. So it started to melt. But also it will introduce some overcooling of the water and may have some like formation of the ice as well. So not fully ice zone, but some ice. And then when I go forward, the more heat will be transferred into the ice region, and gradually the ice melt until completely, right? So after reaching 400 seconds, so 400 seconds, and then all the ice melt. So 400 seconds, that's nearly 10 or 11, or it should be like 13 minutes, and all the ice have melted at such heat transfer condition. So I list all the results here, clearly showing the process of the ice melting. So that is actually a very good application of the phase change by introducing the source item using this solidification melting source. We don't need to use any two-phase or multi-phase flow model. I only introduce the source item by watching the temperature, and we use the porosity ring to simulate the solid, and we can track the phase change. So imagine this is the final change. If you want to simulate the ice formation, you may have results like this. So the ice may be formed like this if it's a cooling process. Now it's melting, so we see the ice melting in the process. And that is called porosity or enthalpy porosity method you can use for the phase change. These two examples here is very good application of using source items for the CHT by using FV options.